Okay, so in this session we will talk about accuracy points and Chebyshev spacing. Let us say we want to do a function generation. Y is a function of x. Okay, this is the function we want to generate. So x is our input and y is output. So this is what is desired. Okay. Now, when we are synthesizing, our synthesis is not going to be exact. It is going to be approximate. Okay. We'll have approximate and not exact synthesis. And due to which the output that we will get y, okay, it will actually not be equal to fx, but it will still be a function of input. So I'm writing it as y. This is output that we are going to get. It will be a function of x, our input, and along with that the design parameters we have. Let us say we have n design parameters, so we can write them as r1, r2, r3 up to rn. Okay, these are our design parameters. Okay, so we have approximate synthesis, and what we are getting is not same as what is desired. Okay, so there is an error, and that error is called structural error. And write this as what we wanted fx minus what we got. Okay, this error is called structural error. Okay, and this error is actually inherent in the mechanism, due to approximate synthesis. But we are not going to get exact. So let us say, if you want to plot it, say y as a function of x. Let us say this is the function what we wanted. This is what was desired. So this is fx. Okay. And say what we got is, let us say, something like this. Let us see. It's not changing the color. Okay, now it is changing. Let us say this is what we got. So this is fx. And difference between these two, that is called structural error, and that is inherent due to approximate synthesis. Now you can see there are some points like this point here. Okay, this point, at these points error is 0. Okay, at these points it is 0. So these points are called accuracy points. Accuracy, or you can also call them precision points. Okay. So when we are synthesizing, say, a 4-bar mechanism or a slider crank mechanism, then, and it is function generation, then in the problem itself it is specified whether you have 2 accuracy points, 3 accuracy points, 4 or 5 accuracy points. And what is important is, it is not that you can have any number of accuracy points. The number of accuracy points will be equal to the number of design parameters at our disposal. Okay. The number of accuracy points cannot be arbitrary. They will be equal to number of design parameters at our disposal. So when we write down equations, let us say we are doing an analytical synthesis, we write down equations, for example, Freudenstein equation. Then we have to see in that equation how many design parameters are there at our disposal, okay, that we can choose. And the number of accuracy points will be equal to that number of design parameters. It cannot be arbitrary. There is another error that is called mechanical error. The first one we talked about, that is structural error. Another is mechanical error. This is not inherent due to synthesis as such, but this error is due to mechanical defects. Okay, for example, joint clearance, uh, inaccuracy in lengths of links, due to those reasons we get mechanical error. Okay, now it is obvious that we would like to minimize. Okay, our objective will be, let us say we have to do a function generation, y is a function of x, and according to the problem we can only have say 3 or 4 accuracy points. Okay, so our synthesis is going to be approximate. uh, only at 4 points our error will be 0, but at other points we are going to have some error, but still our objective will be to minimize the overall error. Let us say error at this point, it is not that it should become too much. Maybe okay, couple of percent, 2-3% may be tolerable, but if it becomes 30%, I won't like it. So apart from accuracy points, our objective is also to minimize, this structural error. I'm just writing ex at known accuracy points. Okay, this is our objective. For example, let us say we are given that the range of input we have to generate y as a function of x. Okay, this is the function, and we are given x goes from let us say 1 to 5, and we have to choose say 3 accuracy points. According to the problem we can only have 3 accuracy points, but we have to do a function generation for the range of x from 1 to 5. Okay, now one question is, see, in this range I can only pick 3 points. Which points should I pick? I can pick say 1, 5, and let us say an intermediate point, but it can be anything like 2, 3, 4. So how to pick accuracy points so that the structural error at known accuracy points is minimized? That is what we want actually. So the question is how to pick accuracy points so that this objective is fulfilled. Okay, it turns out mathematically that if we do this Chebyshev spacing of these accuracy points, okay, then the structural error at known accuracy points, it is not minimized, but still it is close to that. Okay, so Chebyshev spacing of accuracy points gives you can say a a fairly low value of this structural error. Okay, so let us see what is this Chebyshev spacing, and I'm just going to refer you to Ratan for that. Uh, this is described in section 5.9, Chebyshev spacing, and you can read this text, but I'm just going to come to what is this Chebyshev spacing. So here you see, uh, if you want n accuracy points in the range, say for function generation between x0 and xn plus 1, okay, between these limits, let us say you want n accuracy points, then based on Chebyshev spacing, how do you get those points? For that, this is the formula: xi equals xn plus 1 plus x0 by 2 minus xn plus 1 minus x0 by 2 cos 2i minus 1 pi over 2n, where I goes from 1 to n. So you will get n values of x, which are n accuracy points based on Chebyshev spacing. An example is given here. Say we want to generate this function, y is a square root of x, and the range of x is from 1 to 3, and it is said that we have to pick 3 accuracy points or 3 precision points, then x1, x2, x3. Based on this formula, the value of x0 is 1, xn plus 1 is 3, so you just plug those numbers and I will go from 1 to 3. You put those values and you get 3 points, x1, x2, x3, and corresponding to that you get value of y, y1, y2, y3, which is square root of x. Okay, so this is a method to pick accuracy points based on this formula. There is also a graphical approach to that, which is described here, the same Chebyshev spacing. So the method is like this: first you draw a circle whose diameter is equal to the range, so xn plus 1 minus x0 equal to the range. So you draw that circle here. Okay, so this is, you can see that this is like a number line. So and you draw a circle, and within the circle it says inscribe a regular polygon of 2n sides. Okay, so if you want to pick 3 accuracy points, then inside this circle you have to draw a hexagon. Okay, so because 2n will be 6, so hexagon, you can see a hexagon has been drawn here, 1 2 3 4 5 6. Okay, regular hexagon. Okay, and then these vertices, take projection of these vertices on the number line, and then these points will give you x1, x2 and x3. Okay, now actually another thing here is not mentioned. To draw this circle, you also need the center of the circle, and center of circle will be actually xn plus 1 plus x0 by 2. Okay, that will be the center of the circle. So for this example, your range was from 1 to 3, so center will be 1 plus 3 by 2 at 2. Okay, draw a circle with center at 2 and radius equals to 3 minus 1, that is 2 by 2, 1. Okay, so draw a circle with center at 2 and radius of 1. Okay, and then draw a regular hexagon for 3 accuracy points, and take the projection of vertices on this number line or x-axis, whatever you want to call it, and those will be the accuracy points. So this is the method, and one example is given here. Let us go through this example also. It says design a four link mechanism if the motion of the input and output link are governed by this function y equals x to the power 1.5. X varies from 1 to 4. Correspondingly, theta varies from 30 to 120. Okay, this is the angle of the input link. And phi, that is the output link, it varies from 60 to 130. The length of the fixed link is 30 millimeter and use Chebyshev spacing of accuracy points. Okay, and uh, how many accuracy points? It doesn't say. Okay, generally it should specify. So let us see. They have done this problem by taking three accuracy points. So first of all, you get x1, x2, x3 based on Chebyshev spacing. Correspondingly, you will get y1, y2, y3 based on the function generation, the function that is given. Now, from these x1, x2, x3, you will have to get theta 1, theta 2, theta 3. Okay, and for that, in a previous video, I had described that you take a linear relation between x and theta. Okay, so when x goes from, in the problem you see x goes from 1 to 4, theta goes from 30 to 120. So take a linear relation between x and theta, and based on that, corresponding to x1, x2 and x3, you will get theta 1, theta 2, theta 3. Okay, that is what has been done here, theta 1, theta 2, theta 3. And similarly, phi 1, phi 2, phi 3 based on linear relation between y and phi. Okay, so you get those all three values of theta, three values of phi, and then you use Freudenstein equation for analytical synthesis. You plug the numbers in that and then solve by Cramer rule. You get k1, k2, k3, and then in the problem one of the dimensions is given, dimension of fixed link are given, so you use that information and that will give you dimension of other links. Okay, so that then the synthesis is completed uh, based on Chebyshev spacing of accuracy points.